so now that we've talked about friction, we're going to introduce one last resistive force, and that's going to be air resistance. So like friction, air resistance is going to resist the direction of my motion. If I have velocity this way, right? If I'm moving this way, air is going to be pushing this way. But if I'm not moving, I don't have any air resistance because there's no air pushing on it right now. Air resistance only occurs when I have motion. Now, what does air resistance like? Does it cap out at anything? Because I know that friction, right? Friction capped out. The maximum friction was as much as the applied force. Well, that's the same with air resistance. Right? If I had an object and I'm dropping in free fall, its force would be this way, its weight, applied force, and here would be its resistance. Resistance increases, right? Because if I'm moving faster, I have more air pushing on it. But at some point, I can't move faster, right? The faster I move, the more air I push on, so the more air resistance I have. But then, at some point, these two things are going to be equal. Air resistance is going to increase from 0 until it equals out this. Then I have some constant velocity, right? Because then the net force would be 0, so my v would be constant. If my velocity is constant, that means I'm not moving any faster, air resistance can't increase, so that's something we call terminal velocity. At that point, we are not accelerating anymore. That's the fastest velocity we can go in free fall. So yeah, if you're going parachuting and you have some sort of mass, then you can find your terminal velocity. That's kind of cool. So let's say I want to find velocity as a function of time for this system. How would I do that? Well, I'm going to draw the system here, right? R, F, W. And I can write R as something like BV, and while this is equal to mg, where m is the mass of the object. Why BV? Well, B is just a constant because R is proportional to my velocity, for small objects, that is. For small objects, the faster I move is directly proportional to how much air resistance I have, so it's like a line, and B is just a constant that's going to determine, B is just a constant. It depends on a lot of different factors, like maybe the shape of the object, how much area it covers, things like that. So let's set up an equation right now. So we know the net force, right, is the sum of Fw and R. Well, the net force, according to Newton's second law, is ma, and this is equal to mg, right, or it's minus R because they're in opposite directions, minus bv. Now we're going to use a little bit of calculus. So this is physics C after all, right? So ma I can write as change in velocity over change in time is equal to mg minus bv. So I'm going to divide both sides by mg dv, so I get m over mg minus bv times dv over dt, and I'm going to multiply both sides by dt, so that dt goes away, and I get this. Now I'm going to integrate both sides. This side, if you plug into an integral calculator or do some mu substitution, you'll know is, sorry, wow, alright, is equal to m over negative b multiplied by ln of absolute value of mg minus bv, absolute value, plus some constant, we'll call c2, is equal to, integral of dt is just t, so plus some constant c1, right? Now notice I have this absolute value sign here. I actually don't need it because because mg is always going to be greater than bv until they're equal. So this is always going to be positive anyway, so I can just get rid of those absolute value signs and make these parentheses. The next thing I'm going to do is I'm going to combine these two constants into a single constant. So on this side I have negative m over b times ln of mg minus bv is equal to t plus some other constant c. I want to find what that constant c is. And I can do that by plugging in things that are in our variables. What are variables? Well, my goal was to find v as a function of t. So we'll just plug in values for v and t. When t is 0, right, when the object has started its free fall, its velocity is 0. Why? It's just like the thing where I did when I threw up the marker, and I'm like, what is its velocity at the top? It's 0, because it doesn't accelerate until you let it go. So I'm going to plug in 0, 0 to solve for c. So I get negative mb, m over b times ln of mg is equal to c. That's great to know, so we'll just plug that in for c plus negative m over b ln mg. Alright. Now I'm going to erase the top so we have more space, and we're going to start from this equation and work up and work. So what can we do here? Well, I can multiply both sides by negative b over m. And what do I get? I get ln of mg, right, minus bv is equal to negative b over m t. And what happens here? Well, I multiplied by, it's as if I divide both sides by negative m over b, so I divide this side by negative b over b, so I get plus ln of mg. Now I do e to the power of both sides, so e to the power of this, e to the power of this. What do I get? Well, e's and ln's cancel out. E to the power of ln x is just equal to x. So this side, I just get mg minus bv. What do I get on this side? Well, I can split up this into two different things. I can split up e to the power of simply this, multiplied by e to the power of simply this, by using my exponent rules. So I get e to the power of this, e to the power of negative b over mt, multiplied by mg. Alright? So now I'm going to move mg on this side, so I get negative bv is equal to e to the negative b over mt times mg minus mg, right? And then I'm going to divide both, I'm going to factor out an mg, and I'm going to divide both sides by negative b. So you get v is equal to, I factor out mg, mg, right? And then I divide everything by b, negative b. What do I get? I get 1 minus e to the power of negative b over mt. You can check that my work is correct. Multiply both sides by negative b, rearrange. You'll notice these two things are derived from each other. Alright, so there is our function, v as a function of t, our velocity as a function of time. And eventually, right, as t goes towards infinity, when t goes towards infinity, this becomes 0, right? Because this is b e to the power of some negative thing. And the magnitude of that negative thing is increasing. This eventually turns into v is equal to mg over b. Right? So as time is really large. mg over b would be our terminal velocity, because that's our velocity as time is so high, as time increases that the object is almost in free fall. Or that object, or this r, is almost equal to this fw. So there we go. I hope you learned something about air resistance, and if College Board ever tells you to do this derivation, you are set. So have a wonderful day and enjoy your studying.